All right, morning everyone. So we finished Friday's class, starting to look at fluidic systems. So this is going to be, fluidic systems are going to be the last, I would say, class of different types of systems we're going to look at. So I wanted to start to tie together some of those ideas. And so we just began to fill out this table here to try and help draw analogies between the different systems. So we barely got into this. If we have a mechanical system, we have a potential variable. So we talk about force being potential variable. You can think about this in terms of Newton's laws, right? The acceleration is the difference in force, basically in different directions. Just like in a fluidic system, we talk about equations of motion, we have a pressure difference that is potential, right? And that drives our system. Flow variable is the velocity of the masses flowing in a mechanical system. A fluid system is flow rate. And then we have components. So these are variables that we talk about here in terms of something that is a state of the system or something that drives the system. We also have components. So a mechanical system, we often talk about being composed of mass spring dampers. With fluidic systems, we have resistors, we have fluidic capacitors, we have then fluidic inertances. And so we have loss components in a given mechanical system. We have potential energy storage. And we have kinetic energy storage in all these systems. Okay, so in a mechanical system, what's our loss component? What system in a mechanical system has losses associated with it? Friction, right? Right. So we often model that as a damper, right, in a mechanical system. So the damper is our loss component. How about in a fluidic system? What's going to be our loss in a fluidic system? Viscous losses, right? So, so we look at that, when we look at a fluidic system, we say that's a resistor, or fluidic resistor in our system. Okay, so this can either be something that is intentionally causing resistance, like if you have a valve or some sort of constriction, or just pipes in general are going to have losses associated with them, and we have as models of resistance. Mechanical systems, potential energy storage. What do we have? Springs. I heard springs coming from somewhere, right? So that's the element which we store potential energy in this. Okay, then how about in a fluidic system? Accumulator, right? All right. Or tanks. And we'll get through an example of a tank being able to store energy as well. Right? So that'd be a fluid capacitor or accumulator. All right, kinetic energy storage in a mechanical system. What do we have? Masses, right? And then fluidic system. One term we barely introduced it on Friday. It may not be fresh. So fairly similar. It's actually the mass of the fluid flowing. All right, so the mass, we have fluid. It has a certain velocity, right? So it's going to have momentum associated with it. And so this is called, we call this an inertance in fluidic systems. But it's essentially the same idea, right? So you have a solid mass. We talk about mechanical systems. We're usually talking about solids, right? But with a fluidic system, you're actually talking about a volume of fluid moving in some sort of channel or some sort of vessel, and that has a certain kinetic energy storage element to it. Okay, so did anyone go to a super old high school that had clanging pipes? One person went to a super old high school like mine, too? Okay, so in the wintertime, you know, if you ever heard the pipes clanging like crazy, right, that's because of actually poor fluidic system design for you had radiator type heat probably, right? So you had a boiler in the basement, runs hot water or boiling hot water all throughout the building. That's why your pipes clang. So anyone's been like a really old building, they hear like this clanging noise. It's from the inertance of that fluidic system. Filling out these other ones here, in electrical systems, voltage, flow variable of current, loss. Okay, so one thing that students will commonly mistake between in terms of what's a potential energy storage and a loss component between mechanical and electrical systems is that the symbol for a resistor looks exactly like the symbol for a spring, right? And so they think that they act in the same way. So I know it's confusing, and whoever designed this way of symbols many years ago probably should not have done it that way, but these have associated with them. Potential energy storage, we store energy in capacitors. And kinetic energy storage is inductors. Okay, the other type of system that we talked about in this class is magnetic circuits. And this was potential energy, or potential variable is MMF, magnetomotive force. Flow variable is flux. And then we had reluctance. And then the other two, we really don't have an analogy to make there for magnetic circuits. At least as far as this class is concerned. Okay. Any questions about these relationships, these ideas, about how, even though all these systems have very different physics associated with them, very different domains, they have some sort of commonality between them? Yes?
Do people ever draw like equivalent circuits for a mechanical system?
I've never seen it. No. You could, though. It's not common practice. So our common practice with mechanical systems is we start from free-body diagrams. And so that has been pretty well established. You don't see electrical circuit diagrams, as far as I've seen. I don't. Yeah. Not to say that no one's ever done it before, but I've never seen it. Okay, so let's get to some examples. I wanted to get through both of these ideally. Maybe your homework leverages them. Okay, so first example here is we have a system. It's pretty simple, but we have a pump. A pump is what it's doing is it's taking pressure from ambient and it's elevating the pressure. So we have a pump and it increases the pressure from the low side, basically just a tank of fluid it's taking it from, and then in the high side it has some sort of higher pressure to it. The system's pretty simple. It has two orifices which create a higher resistance, and it has an accumulator in the system which has a capacitance associated with it, and then it dumps into this. All right, so this is asking just calculate the pressure at the accumulator in the hydraulic circuit below. Assume that the inertance of the fluid is negligible. So this will oftentimes be, sometimes the inertance of fluids will be negligible, sometimes it won't. It'll be basically based on how large the system is. So if the system is containing a lot of volume, it's going to have an appreciable inertance to it. If it doesn't have a lot of volume, it will not. Okay, so length of pipe, L. Okay. So what we have here is we have a few things going on. We have pipe, length of L, ID of D along this length, and also we have, so this has a normal resistance associated with it from basically the viscosity of the flow. When we get to the orifices, that constricts even more, that has a higher resistance, and then we have a pipe of a length L, ID of D on this side as well. And so our first step for all of these is going to be to write this as an electrical circuit analogy so we can try to understand and analyze this much like we would do an electrical circuit. So if we look at these analogies that we had over here, we have a fluidic system, we have a potential variable, which is pressure. So if we were looking at electrical circuit, we would call this a voltage source. The low side of this voltage source is at ground, or P is equal to 0. All right, so this is not absolute pressure is equal to 0. This would be basically atmospheric pressure in reference to the pressure that's all around us right now, right? Okay, so we have this pump. It generates a pressure of PS. So that means the low side is at 0, the high side is at PS. And then it's going into our fluidic circuit. The first element is that we have a pipe here. And this pipe is of length L, IDD. But we can lump this into a single resistor. And we'll get into what our pipe is in a second. But it's first going into this resistor. Then we have this orifice that it goes into. So this is going to be another resistance. And then we're going to get into the accumulator. So I'll talk about this in a second, but we have now a pressure node as drawn on this schematic here of PA. Right? So first thing that happens, fluid comes out of the pump. It's going to have a certain flow rate associated with it. We haven't solved for that yet. But it's going to go into a pipe with a resistance, orifice of a given resistance, then into the accumulator. And so now we need to decide how to draw this accumulator. Right? So we know from this table on the left-hand side that accumulator is going to be represented by a capacitor. So let's just draw this as a capacitor. And the question is, at what end do I attach the other end of the capacitor? Ground. So why ground? You're right, but why ground? Yeah, there's no flow going through it. So, yeah, so I agree. So there is flow going into the accumulator, right? Yeah. Yeah. Okay. So yeah. So I agree. I think both answers are right. But then, in terms of if we look at this from the potential point of view, as we look at the system before it starts, right, is all at rest. So you can say there's maybe some fluid in it, but it's not pressurized. And now we're going to turn on this pump. And so now we're referencing the charge in this accumulator to ground, right, because it starts at ground. Right, so we're going to have this capacitor connected, where at one end it's going to be PA. That's where it's actually physically connected in terms of its inlet is connected to this tap at PA. And then the other end is going to be at ground because the storage of pressure in the system is going to be referenced to atmospheric pressure. Okay. Any questions or ideas? This one trips up students quite often. Okay. All right, so then the right-hand side of this looks a lot like the left-hand side. All right, and then it ends, if you look at what happens at the end of the pipe, it's back to atmospheric pressure, and so this would be referenced to ground again. Yes?
If they stated that the accumulator had a pre-charge of some pressure, would we still put it at 0?
So if you said it had, like the fluid line has some sort of pre-charge, right? So that would be represented by, you could think of it as, a pre-charge would be in terms of the voltage level. This would look like it. Especially if it started at static, you could represent this as, like, say, a battery. It says this holds the other end of that capacitor at some elevated pressure. Okay. So this is then R2, our pipe. Q1. Q2, so I'm just labeling variables here, so this is not given in the problem statement, but sometimes it helps to make up variable names. So we want to understand what is the flow rate through the left-hand side of the circuit, through the accumulator, and also the right-hand side of the circuit. And then just note, this was given, I think this was given on Friday. If not, here it is. This is the resistance of a pipe. So when we say pipe, we mean circular cross-section. So if it doesn't have a circular cross-section, this equation does not apply anymore, of length L and ID of D in laminar flow. So that means that we have R is equal to 1/28 mu L over pi d4. So I don't know if you've gone through this in your fluid mechanics class, relationship between pressure drop and flow rate through some sort of circular channel, but this is the relationship. Yes?
Will it always point out, like, there's like a length of pipe, like here that you have to account for the resistance, or is there like a common, like, between two elements you assume?
Yeah, so the problem statement would specify. Yeah. So sometimes, and it's all about, I guess, orders of magnitude relationships too. So some pipes are, like if you look at the resistance here, it's a function of diameter, right, and length. So if the diameter is really large and the length is really small, the resistance is not going to be very important, right? Or if the viscosity is really large, right? So if you're pumping hydraulic fluid oil as opposed to water, they have a pretty different viscosity associated with them, right? So it'll be given the problem statement of whether or not it's appreciable or not. Yes?
In our fluids class, we usually talk about like a pipe, and then if you had a smaller pipe, you'll get a change in pressure and flow rate. But then if you enlarge the pipe to the original size, everything would go back to the way it was before. I think so. Is this something different because we have like resistance now, like resistors, and you end up going, like you lose pressure all the way back to zero. Although it's not like we're changing the size of the pipe necessarily. We're putting like valves in, and you lose pressure over the pipe.
So maybe I'm missing the question.
Like in Bernoulli's,
Okay.
we sort of assume that there's no. I guess we're assuming there's no like energy loss.
Yeah. So like Bernoulli's equations, you're looking at basically different locations that the pressure is a function of velocity, right? Bernoulli's equations. So that is, yeah, I think you're getting to maybe one of the fundamental differences of the way we look at fluid mechanics in this class versus that class. So that class, you're looking at, the best explanation is you have some sort of system, right? Like you have some sort of flow going, and you have some sort of free stream flow, and like the really common problem you've probably seen is you have some sort of ball, right? You're looking at what's the pressure here. Have you gotten problems like this yet or no? Okay. Okay.
It's just like we have something that looks like a resistor, like the pipe gets real small and gets big again.
Okay.
But it's not like we lose pressure on the other end of it necessarily. Like it goes back to the same pressure as it was on the other end of it. On the other end of that little small thing.
Okay. All right. So similar idea then, I guess. So you'll get to problems like this. Trust me. You'll get problems like this. This is some idea. You have a loss of basically cross section of your flow here, right? And so you have the highest pressure. You'll see this when you get to this. You have the highest pressure right here. This is where the flow stagnates. That's the highest pressure point. And so then you're going to have essentially same pressure, but highest pressure here. So that I would say is for the perspective of you are looking at mapping out what is the pressure at any point in this fluid flow, right? In the way we look at this class, it's called lump parameter analysis. You know, we call it that. This would be P1, and this would be P2. We're essentially ignoring everything that happens in this region, and we're calling that this acting just as a resistor. Right. And so then the pressure will be lower as long as this cross section stays the same. The pressure will be lower at P2 than P1 because we had something that had a resistance associated with it, like electrical circuit. Even though as we go along this path, the pressure is going to be highest here. So if you look at the pressure, be continually decreasing. It's going to spike here at the front of this, and then come back down as we get to the back of this sphere, but it's going to be continually dropping across this channel. So we're not looking, I would say this is more of a global perspective, where your fluid mechanics class is a local perspective on pressures and flow rates. Does that make sense? Kind of the the different way in which we look at it. So if we wanted to, in this class, if we want to look at like all the intricate details of what pressure is happening and everything, we would not be able to get to systems analysis. So we're kind of saying lumping certain parameters together, looking at these as individual components and trying to understand how the entire system works together. Yeah, so we're considering flow rate, which is tied to velocity, but we're looking at a lumped flow rate, which is, in the velocity we were looking at, here's a pipe in the center, say we're looking at the velocity. Here we're looking at more of the velocity as a whole. Bulk properties. Okay. All right, so here's our circuit. We have values for our pipe given the viscosity, length, and diameter of the pipes that we're looking at. And then the question is, how do we get to the answer, which is we want to know what is the pressure. Just to remind you of the question again. Calculate the pressure at the accumulator in the hydraulic circuit below, right? Given this setup. Okay, so just like we did with magnetic circuits, we're going to be often looking at, and also electrical circuits we're looking at using Kirchhoff's laws for all of these. And so the very first thing we're going to do with this is we're going to look at the node A. So we look at Kirchhoff's law. So Kirchhoff's law applied to node A. Oh no, cancel. All right, so Kirchhoff's law applied to node A. Remember, Kirchhoff's law is either, you can say, the flow into a node in a circuit is equal to the flow out of that node, or you can say that the sum of all the flows is equal to 0. So we label these Q1, Q2, Q3. So this is going to give us Q1 minus Q2 minus Q3 is equal to 0. Our Q1, all right, so Q1, we can look at this in terms of Ohm's law, which is basically the current running through a resistor. So we have V is equal to IR, or I is equal to V over R. So the potential drop over this left leg here is going to be PS minus PA. And then we have resistance of our pipe. I'll just make it RP to make it shorter. And R1, because these two resistors are in series. All right, let's go Q2. So just a reminder, in terms of the voltage drop across a capacitor. So if I have a capacitance of value C, voltage drop, current, the relationship is that I is equal to C dV dt. So in this case, we have then that the flow rate, which is our current variable, is equal to C. Sorry, I forgot to give that in the statement up here. Let me make sure that, yeah, C. C dPA dt. And then Q3 is going to look a lot like Q1. PA over RP plus R2. Yes?
We have a function for the velocity, for the, like the voltage of the capacitor. Because I think we would need that if we were doing KVL, right? If we were doing KVL, then we
Yeah, so that your question is, if you wanted to look at this from the voltage law, how would you write the voltage drop across the capacitor?
Yeah.
So we would just rearrange this equation here. So we'd have that V is equal to 1 over C integral I. So basically integrating both sides to get V on the right-hand side. Oops. Okay, so putting all these equations together, okay, so our output of the system, the question asks, what is the pressure at the accumulator? That's PA. Then the input of the system is the pressure of the pump. Okay, so rearranging a little bit to get everything that's an output on the left-hand side. So just rearrange this equation. You have d PA dt plus PA, and we have 1 over C, so I divide by C to simplify this. And then I'm combining all the resistances, getting these under a single common denominator. Okay, so here we have what we have is a differential equation. So what we've taken is some sort of configuration of fluidic system, trying to understand this from an electrical circuit analogy. And here we get then a first order differential equation, and it's a non-homogeneous differential equation, right? So we have a homogeneous function, a homogeneous term driving the system. So in a form that looks a little bit more like what you may have seen before, we would have the differential equation dPA dt is equal to 1 over tau, which is the time constant of the system. PA is equal to K PS, right? That would be the more standard form you'd see, maybe for differential equations course. Yes?
Like, how do we know that we wouldn't want to move over the 1 over C, that factor that's multiplied by the pressure source? You would want to bring that over to the rest of it. Is it because standard form, like the dP over dt has to be on its own?
Yeah, so you'll see, so when I say standard form, I would say a standard form. So sometimes you'll see the tau on the dPA dt term. And sometimes you'll see it as 1 over tau on just the PA term. So this is just getting it into one of the forms that's more standard and trying to get rid of a lot of these. It's a lot to look at all these variables and what I'm trying to make sure is everyone can see that this is a first order differential equation. So I'm stripping away a lot of the variables and writing in terms of a time constant, which is, I hope, a little bit more familiar to a lot of people. Yeah. So we could have had the coefficient on the dPA dt as well. So then a little side question is, okay, so assuming the pump turns on at t equals 0 and instantly creates a pressure PS bar. I'll write the little bar on top of this in a second. Find PA T. P sub A of 0 is equal to 0. Okay, so PS bar. So this would be a common idea, right? If you were to have a system initially at rest, right, all the system is completely depressurized. All of a sudden, you flip on the switch to a pump. It all of a sudden starts pumping the system. What is then the pressure at the accumulator in time, right? Would be the type of question we're looking at. So when we're describing this type of pressure, what are we referring to? What does the signal PS look like? We say that the pressure PS, the pump turns on at times equals 0, and instantly creates a pressure of PS bar. What kind of function are we looking at there? Karsten. A step function, right? So what we're saying here is that we have the pressure coming from the pump. Oh, no. Okay. Wow, why won't it let me do that? Okay, we're just going to have some sort of stray lines in this plot then. Okay, so we have PS at times equal to 0 is off. And then at time 1, it instantly turns on, and this has a value of PS bar, right? So it looks like a step function. So obviously a pump can't just automatically just create a pressure of this value without some sort of transient, but this is a simplification to try and understand approximately what would the pressure signal look like at the accumulator. So all initial conditions are equal to 0. So that means to solve this, you can use methods that you will learn in your differential equations class, say sophomore year, or you can also use Laplace transforms if you want. And so we'd have then S, PA of S, plus 1 over tau, PA of S. Sorry if that wasn't clear. I decided to use the Laplace transform method, not something you would see in your differential equations class. K, PS bar, plus U, over S. Right. So that means then that PA of S, K, PS bar, 1 over S, S plus 1 over tau. Okay, so this is a very common Laplace transform. If you look in any Laplace transform table, will have this relationship that we have in the time domain. You have 1 e to the negative at. If you go forward Laplace transform or reverse Laplace transform, you jump between these two, and then this is a s over s plus a. So we can rewrite our expression for PA of S is equal to tau K PS bar 1 over tau S plus 1 over tau. To make this look like our Laplace transform table entry. And so that means that doing the inverse Laplace transform of this expression gives us then PA T is equal to tau K PS bar 1 minus e to the negative T over tau. So just to note visually what this looks like is we have okay, so if we look at this, we should have an initial pressure of 0, right? We said the system starts completely depressurized. So if I plug in time is equal to 0 in this expression, I get e to the 0, which is 1. 1 minus 1 is equal to 0, right? So as I start, I plot, it starts at 0. If I look at time goes to infinity, if I want to know the steady state response of this plot, e to the negative infinity is 0. That means my final value for this plot would be tau K PS bar. Okay, so what this means, I guess the most easy thing you can see of this is that we increase the pressure of our pump. For some reason, either we change the operation of the pump or we buy a different pump that pumps to a higher pressure. The accumulated pressure will go up. That makes sense, right? And then also we have this transient in between, which is our standard first order response or exponential response. So then asymptotically or exponentially approaches this steady state value. Okay, so we turn on the system, pressure spikes quickly, and then it slowly then converges to the steady state pressure of the system. Okay. Any questions about this example? Okay, let's get to a more difficult one then. Okay, so fairly similar, but it has a few other elements in this. So, same idea, we have some sort of pump. It's taking your pressure from sort of ambient. It's then filling up two different reservoirs. So you can think of it as some sort of municipal type system that's filling up these reservoirs and it's dumping it back to ambient again over here. So we have resistance associated with this length of pipe here given by R1. The distance between tank 1 and tank 2 is said to be really long. And so it's going to have a certain inertance to it, and that the flow has a lot of mass, therefore inertance. And then we have resistance flowing out, and then we have tanks that we're filling up. And these tanks have state variables of what is the height of those tanks. And so what we want to do is we want to find the transfer function between output QF and 3 different inputs. Oh, sorry, I forgot to mention that these tanks are open, so you can get rain as well. So rain can fall into these tanks. And those are given by functions Q1, Q2, Q3. So not only are they filled by the system, but also they're filled by some sort of external fluid dumping into the system, like Q1 and Q2. So similar idea as before. We want to first start off by drawing the electrical circuit analogy for this. So some of these elements are going to look very similar. I'm going to fill those in quickly because those look a lot like the previous example. But we have some sort of pump which gives a pressure source, P. We have a resistance on the first leg, R1. All right, and then we get to a storage element. So the storage element is this tank. Okay, so the system we didn't have any rain coming into the system. It's completely depressurized. It would have a height of 0. It would drain out of the system, as you can see here. So this is in reference to ground. So I say this is C1. The next length has, it's a little more complicated because we have inertance associated with it. We get to our next tank. C2, and then we look at the very end. And this is R3. All right. And I've missed a critical component of this that we're going to throw in a second. But just to label these, inertance, this is then R2. We have our two different tank capacitances. And then the next thing we have is we have fluid dumping into the tank as well. All right, so this says that we have fluid dumping into tanks 1 and 2, and this is specified by a flow rate. So what type of symbol in electrical circuit are we going to use instead? Sorry? A diamond? Not sorry, a diamond. It's still a circle, but we have a different symbol instead. So we have a pressure source, or sorry, voltage source usually has plus minus, right? So here we have a flow rate source, right? So this would be equivalent to a current source in electrical circuit analogy. So same in terms of, these are usually circles, but then they have, instead of plus minus, we have an arrow going through them to indicate that this is a current source. And we can reference this all to ground if we want. That's Q1. And Q2. Okay. Any questions about the electrical circuit analogy? Yes?
How do we get the capacitors?
So,
They're stored tanks.
yeah. Yeah, so these are tanks, and therefore they store pressure, right? So if we look at this like kind of swimming pool analogy, bottom of your swimming pool has the highest pressure. This is a tank. We're filling up the height of the tank, and that's creating a pressure at the bottom. All right, so just like the accumulator, which you're storing an elevated pressure, right? Here we're storing an elevated pressure as well.
If it rains, the pressure will get heavier unless they dump a bunch.
Yeah. So it's still a capacitor. It's still storing the pressure in the system, right? But now we have, the rain is indicated by this fourth leg of this node here, which is dumping in this case, flow rate, right? All right. So again, Kirchhoff's current law for each of these. I have then, I need to start to label things. So we have Q1 or Qin, and then I can say, how do I label these? This one's Q1, we'll call this one Q3. The question ultimately asks, what is the outlet flow rate? QF. So label as QF. We look at tank 1 as our node. All right, so we have Q1 is coming in. We have also what's coming in is P minus P1. So make sure we label this node P1, P2. This is divided by R1. We have then Q3 coming out. We'll get into what Q3 is in a second. This is a fairly complicated expression, so we'll just leave it as Q3 for the time being. And then we have then pressure, or basically the fluid flowing into the accumulator or the tank, and we'll take a look at what that is in a second. So tanks are actually a little bit more simple to analyze than capacitors, in that you don't have to memorize this equation for it. You can actually kind of use geometry, right? So this tank, forgot to mention, the problem statement has area A1. So A1, A2. So it has area A1. And so then if we want to know what is the flow rate in a tank as a function of the state variable of the tank, the state variable of the tank is the height of the fluid in that tank. Right? So if I want to know what is the volume of the tank, right? Volume of the tank is A1 times H1. Right? And if I want to know then what is the volumetric flow rate of flow going into this tank, that would be A1 dH1 dt. So that is the amount of fluid that's stored in this tank, in terms of the rate at which fluid is stored in this tank here. Okay. Last thing is that having P1 and H1 are redundant, and so we want to try and work with as minimal number of variables as possible. So that would be P1 is equal to rho G H1, from what you probably went through stuff like this in your fluid mechanics class. So then, simplifying this expression, I have Q1 plus P minus rho G1, or sorry, G H1 over R1 minus Q3 A1 dH1 dt equal to 0. All right. Tank 2, similar expression. All right, so I have Q3 coming in. I have Q2 coming in. I have flow coming out in terms of pressure loss. Or sorry, flow coming out in terms of that's in my output of my system. And I'm going to write this in terms of P2 over R3, and I hope this becomes clear towards the end of this problem, why this is the case. But we're trying to work with as few variables as possible at first. And so even though we ultimately want to find QF, it makes sense to work with the state variable and pressure. And then same idea, A2 dH2 dt is equal to 0. Okay. Then lastly, we have this kind of unknown Q inertance equation. So let's fill this in. Inertance equation so we have this pressure drop P1 to P2. If I were to express this pressure loss P1 minus P2, I can use Kirchhoff's voltage law, which is the pressure drop across an inductor. So the pressure drop across an inductor is equal to the inertance times the current through the inductor, or change of current with time of the inductor. And then I have then the pressure drop across the resistor, R2, which is given by Ohm's law. All right, so now I have this relationship between P1 and P2, given this inertance. Okay, so what we have here is we have three equations. Unknowns that we have unknowns of P1, P2, and Q3. Okay. Actually, we wrote this in terms of H's, so sorry about that. We have this in terms of H1, H2, and Q3. I say that because we can interchange the pressures and the tank heights. These are kind of interchangeable, right? So the pressure is directly given by the tank height. So I can work in terms of these H variables instead if I want. And so we have 3 unknowns, 3 equations. This is solvable. And in the last 5 minutes, I can at least start to set this up. I don't think I'll be able to get all the way through it. So just getting these, making sure the 3 equations are very clear. We have Q1 minus P minus rho G H1 over R1 minus Q3 minus A1 dH1 dt is equal to 0. Q3 plus Q2 rho G H2 over R2, or sorry, R3. Then my inertance equation. All right. So if I take the Laplace transform of all these, yes. Yes, thank you. Thanks. All right. So I think we only have 3 minutes left, so we're not going to be able to go through this complete problem. But I'll talk a little bit about strategy, I guess, in terms of this looks a lot like some of the problems that we looked at for the motors, the motor circuits we're looking at. So the first thing we're doing in terms of strategy is the question asks for a transfer function, right? So as for a transfer function, we're looking at the Laplace transform. So in terms of steps to solve this, so first step, let's take Laplace transform. Second one is going to be then solve for, and then the variable that we're interested in here is important. So what the problem is asking is it wants you to find what is the flow rate out of the system in terms of this QF. Okay, so if you notice, nothing here is in terms of QF, right? But we do have a variable that is statically related to QF, and that the flow rate through this last resistor is equal to the pressure drop across the resistor over its resistance value. Right, so we have a static relationship. So we have that P2 is equal to R3 QF, right? And so solving for P2 is just as good as solving for QF, because then all you have to do is divide by R2 and R3, and then you have your answer. Step 2 is going to be solve for P2 or H2, because then those are also statically related as well, given by rho G. And then the last one is going to be that basically then compute P2, compute QF, which is just then multiplying by a certain constant to do so. Okay, so in terms of the next step of this, is going to look almost identical to some of the problems you've been working with electrical circuits. Same idea. I just want to kind of map out the whole procedure. All the detailed notes of how to do this are in the note sets themselves. The main thing is the procedure. So any questions about the procedure here in terms of what you would do next? Okay. All right. See you on Wednesday then.